Hello, this is going to be part 3 of my series determining when a time lapse was taken. And if you haven't watched the previous videos, I would recommend that you do, because I'm going to carry on where I left off. Did you ever find yourself in a situation where you're investigating something, and the more you dig, the more problems that you find, making you doubt your previous results? Well, that's where I seem to be right now. As of yesterday, one of the things that I noticed about the time lapse was that it wasn't taken at a consistent interval. Instead of analyzing every frame individually, I decided to skip ahead every second. So I know that the video was shot at 25 frames a second. So I started at 290 and I compared the transition of the moon to where it was at frame 315, and I measured the number of pixels in between. So for example, this is frame 440 and this is frame 465. I measured the one point which was just on the inside of the crescent to roughly the same spot on the inside of the crescent over here. And so this is 23.9, which would be for 465, so 23.9. And I had done that until the moon had gone down to the horizon. Then at some point, I think I switched to Venus. These are the frame counts at 25 frames a second. So I calculated the number of pixels that the object should have moved in each frame, frame by frame. And most of them were around 1 frame a second until we got to about frame 640. At that point, at frame 640, it started to increase and then it decreased again. So it definitely seems that there was some kind of manual intervention related to the interval timer. Whoever took the video decided they wanted to change the interval rate and changed it multiple times. Either that or they selectively removed a number of frames after they had taken the entire time lapse, possibly to shorten the length of the video. This morning I wanted to see if I could narrow the result down a little bit more using the Skywalk app that I have. So one of the things that I did was I used the lines that I had created previously and I extended them over to Aldebaran and to Venus. I was interested in the difference in declination as opposed to the difference in right ascension. And I'm pretty sure that I got it lined up reasonably well. You can see that Venus is tracking along that line. You can see the stars as they move along tend to be tracking along the other lines. So at this point, if I wanted to calculate the difference in declination, I would just measure a line from here to here and find the shortest point, maybe 226, 227. This line here was for Aldebaran. This line was for the moon, as you can see here. And so the calculations that I ended up doing were, I counted 227 pixels between the declination of Aldebaran to the declination of the moon, and I then converted that to what should have been about 6.79 degrees, since I had previously worked out the pixels per degree. The moon right ascension was the angle that I had worked out to here, and instead of working out the value for C, I decided to work out the value for B. So I had figured that at that point, the moon should have appeared in the celestial coordinate at the right ascension of 39.65 degrees and a declination of 6.79 degrees. And I've also converted that in degrees, minutes, and seconds. And then I tried to load that into my Skywalk app and to find out exactly where the moon would have been at those coordinates using the Skywalk app that has a much more accurate algorithm to calculate the position of all of the objects. And what I found was that it was closer to midday in Europe. It came out to just before sunrise in North America. So I knew there was something definitely off, and I went back to revisit some of the other things. And so one of the things that I did was I wanted to see whether or not the moon going towards the horizon was impacted by atmospheric refraction. And I chose one of the earliest frames that I could with Venus still visible in the frame, and then I measured this value, got a number that I wrote down, chose the next one. 25 frames later, measured it again, took the next one, measured it again, and put the values over here. And I noticed that they were consistently getting closer and closer together. And once again, that's when I realized that the moon is moving in the sky constantly relative to everything else, and that I have to choose the right frame. So then I went back to my stacked images that I had created earlier. This was one of the frames that I had chosen, which was still fairly close to sunset. And then of course here's the one where the sun is just still barely visible. So what I wanted to do was, ignoring the position of the moon, I wanted to find one of the earliest video frames that I could where I could see any star at all. And that happened to be frame 580. And so I just basically started near the beginning and I went ahead until I saw any star at all. And it was this one over here. One of the other frames, 631, that I'm looking at has Venus over here and a few other stars. But you can see that you've got this star and you've got this other one over here, and you've got a few others as well. So back to this one, this star happens to be this star over here. So I created a layer that would be between this image and this image, and I anchored on this star over here. And that's when I realized that there were a number of other factors going on that I had not considered before. And so I did my best to line up this frame with this frame. You can see in this one that all of the stars seem to be separated more than the stars seem to be separated in this one. So it's almost like this one is zoomed out slightly and this one is zoomed in a little bit more, just enough that they're not quite lining up with each other. And if I were to extrapolate the zoom level for the stars and rescale this image to match these stars lining up with Venus, then the moon would be over here somewhere as opposed to over here. So in fact, the moon should be down over here relative to this image. In terms of atmospheric refraction, I looked it up some time ago, and it really only becomes a problem a couple of degrees above the horizon. And anything more than 5 degrees or thereabouts, the amount of refraction is so negligible it can pretty much be ignored. So I was looking at whether or not the guy zoomed in or not. If I compare one of the last images that was taken against one of the first images where I could see any star at all, and I look at the ground, I already mentioned this yesterday, the ground seems to be in the same spot the entire time. So it doesn't appear like the guy zoomed in or not. I'm starting to think now that as the heat of the day was dissipating, it was creating a change in atmospheric refraction and causing everything to, I don't know what the right term is. So that's where I am, and I think that I've spent a little bit too much time thinking about this problem this weekend already. I'm going to have to take a break from this and do other things. I do plan on coming back to this. I do want to think about a few ways to simplify the process of analyzing it, possibly integrate something else in my app that lets me load each frame one by one, click on the various objects and track it through time that way, then apply a polynomial function of some kind to be able to extrapolate more frames instead of having to analyze every one by one, and to be able to determine what the most likely fit would have been for any point in time. But that's it for now. Thanks for watching. I'd appreciate the thumbs up, and I'll see you again in another video soon enough. Bye for now.